So we're back, and you can see here that I have redrawn the normal distribution from the last page. And so this is a probability distribution that tells you the probability that some number of items is going to be stolen from, say, some big box store in a month. And this tells you that the most likely number of items to be stolen, your mean, is 65. And the further away you get from 65, so more items going towards the right or fewer items going towards the left, the less likely it is that that number of items will be stolen. The area under this curve as I mentioned, is going to be equal to 1 total. So right now I'm just going to shade in all the area that we have under here. Say the area equals 1. Now what I want you to start doing is thinking about the area under the curve as a probability. So if I have everything under the curve shaded, my area equals 1, that means that my probability also equals 1. Or 100%. How do you interpret this? Well, there is a 100% chance that some number of items will be stolen. So we're looking at the values that are included in the shaded area here, and technically we're including any possible value that you could have. If nothing is stolen, if 1,000 items are stolen, it's included in this. So the total area under the curve is going to be equal 1 because there's a 100% chance that you're going to have some outcome. Again, there's some number of items that are going to be stolen. And as a quick note here, I'm drawing this bell curve, but technically every normal curve actually has a shape like this, which is that it stretches out to infinity in both sides. So I'm showing a snapshot, but you can imagine that the normal curve actually stretches out to infinity and tells you, there's just a very, very low probability that you're going to have a number that's really, really far away. So again, with this one, we have the entire area shaded for an area of 1, and that corresponds to a probability of 100%. But let's think about this in another way now. Let's say we want to know the probability that fewer than 65 items are going to be stolen in a particular week. So I'll label this again, number of thefts, and this one probability. So if I want to find out the probability that fewer than 65 items are going to be stolen, I want to think about the area under the curve that applies to values that are lower than 65. So from 65 to 0, which is the lowest number you can have, unless I guess somebody's bringing items to the store, which they're probably not. So here we're thinking about the area under the curve that is less than 65. So something that we mentioned before is that this curve is symmetrical and the mean divides it in half. This means that the area on this side of the mean is equal to exactly 50% of the total area, or an area of 0.5. So our total area is 1, and half of 1 is 0.5. So we can say that based on just our knowledge that this is a symmetrical graph, the area under the curve that corresponds to values that are at 65 or less is going to be equal to 0.5. If our area is 0.5, our probability equals 0.5, and we can say that there is a 50% chance that 65 or fewer items will be stolen from the store in any particular month. Again, so what we're doing is we're using the area under the curve for a particular set of values to tell us what the probability is of getting one of those values. So 50% chance of 65 or fewer items being stolen. And I'll add up here a 100% chance of any number of items being stolen. Alright, so that's the basics of area under the curve and how it corresponds to probability. Now I also want to come back to this idea of the 68, 95, 99.7 rule. And I'm going to switch over to a new sheet for this one, but I'm going to be sticking with the same example. So what I talked about on the last slide is the idea that we know the proportion of area under the curve within 1, 2, and 3 standard deviations of the mean. So I'm going to start with 1 standard deviation of the mean here. So I'm going to draw out our normal curve, do it a little bit differently this time. And so this is going to be the theoretical version. So here we have our mean. On the x-axis we have our mean plus 0. Here we're going to call this our mean plus 1 standard deviation. And here we're going to call this our mean minus 1 standard deviation. So this is telling us that for our values here, this is our mean plus 1 standard deviation, this is our mean minus 1 standard deviation. And based on a general property of the normal distribution, we always know that the area in between the mean and 1 standard deviation on either side, so in a positive or a negative direction, is going to be equal to 0.683, or 68.3% of the total area. Here's how this helps us when we're looking at standard deviations that have actual numbers plugged in. So we've got our number of thefts, our mean here, this is 65, and we know that we have a standard deviation of 15. Well, we can start mapping on what we see on the graph on the left here to the graph on the right. So for the graph on the right, we now want to fill in our mean plus 1 standard deviation. To get there, we're going to take 65 and add our standard deviation. So this is 65 plus 15, which comes out to 80. For our line on the left here, we want to know 1 standard deviation going in the negative direction, so we're going to subtract 15, which is our standard deviation, from 65. So here we have 65 minus 15, which gives us 50. So here these lines are at 50 and at 80. We're going to fill in the area between them. We're going to say this is equal to 0.683, because this is always going to be the case no matter what numbers are plugged in for mean and standard deviation. And now we can read this as saying that we have a probability of 0.683 that corresponds to our area of 0.683, that between 50 and 80 items will be stolen. So I'll just write this out. Our area is equal to 0.683. Our probability is also equal to 0.683, because these things are always going to be the same. And so we can say that there is a 68.3% chance that between 50 and 80 items will be stolen. Now we can also do this for 2 and 3 standard deviations away from the mean. So I'm going to draw these graphs out as well. So let's look at 2 standard deviations away from the mean. And this is the point in the class where you learn that my art skills are not great, so all my graphs are always a little bit wonky looking compared to each other. But pay attention to what the lines say and not exactly what they look like. All right, so here I'm going to draw outlines for 2 standard deviations going in either direction. So I'll say this is a 1 standard deviation jump, and this is a 1 standard deviation jump. And I'll do the same thing going in the negative direction. So each of these lines corresponds to a 1 standard deviation jump in either direction. So we can refer to this as mu, or mu plus 0 if you want. And then this is mu plus 1 standard deviation. This is mu plus 2 standard deviations. So again, we're going out from the mean 1 standard deviation to 2 standard deviations. We can do the same thing going in the negative direction. So here we have mu minus 1 standard deviation. Here we have mu minus 2 standard deviations. And when you're looking at a normal distribution, thanks to our handy dandy rule, we know that the area under the curve in between these lines, so within 2 standard deviations of the mean on either side, is always going to be equal to 0.955. And as a quick note here, I will tend to write things out to the 3rd decimal place when I'm doing this, but going out to the 2nd is fine. As always, just show me enough decimal places that I can tell what answer you actually got. All right, so here we have our area under the curve being equal to 0.955. If we plug in our actual values here, we can then figure out the probability of different numbers of items being stolen based on our 2 standard deviations out in either direction. So we're going to say our mu or mean here is going to be 65 again. And now we're going to draw outlines going 2 standard deviations in either direction. And our standard deviation is still 15. So here, we know that 1 standard deviation in this direction gives us 80. 1 standard deviation in this direction gives us 50. And again, I got this from 65 plus 15 and 65 minus 15. Now we're going to go out one more jump of 15. So to get our next value here, we're going to take 80 and add 15. So we're just adding 15 to this value of 80 here, and that gives us a value of 95. So we have now jumped 2 full standard deviations away from the mean in the positive direction. So we did a jump of 15 here and a jump of 15 here. We're now going to do the same thing going in the negative direction. So we had a value of 50 for 1 standard deviation in the negative direction. So we're just going to subtract 15 again so that we can do another jump of 15 out towards the negative side, towards the left. So let's say 65 minus 15. So we do 50 minus 15, and that gives us a value of 35. So I'll shade in all this area, and you can probably see where I'm going with this now. The area between these 2 values is going to be equal to 0.955. Again, thanks to this handy-dandy rule that we have here. With an area of 0.955, we have a probability of 0.955, and that tells us that we have a 95.5% chance that between 35 and 95 items will be stolen. And I'll just start this. So that's the second part of our 68, 95, 99, 7 rule. And for this last one, I'm going to write it out, but it's going to be the same procedure, same thing. So I'll go a little more quickly through it. So here we're looking at our normal distribution. We've got our mean, and now we're going to think about 3 standard deviations going out in either direction. So here's our mu plus 1 standard deviation, mu plus 2 standard deviations, and mu plus 3 standard deviations. Going towards the negative side, we have mu minus 1 standard deviation, mu minus 2 standard deviations, and mu minus 3 standard deviations. And again, I apologize for my terrible artistic skills here. So now we're going to use this. Oh, and we know that the area under the curve between these things is equal to 0.997, or 99.7% of the total area. And again, each of these represents a 1 standard deviation jump in either direction. Keep my notation consistent. All right. So we can apply this to our thefts example now and find out the probability of, the number of items being stolen that falls between 3 standard deviations on either side of the mean. So we've got our mean here, which is 65, and I'll label number of thefts on both of these. and our probability is what's on the y-axis. So we can do the same thing that we did here. We know that a 1 standard deviation jump out towards the positive side brings us to 80. A 2 standard deviation jump brings us to 95. And then to get our 3 standard deviation jump, we're just going to add 15 to 95 here, and that's going to bring us to 110 items. Going in the negative direction, we know a 1 standard deviation jump towards the left brings us to 50. Another 1 standard deviation jump brings us to 35. And then we're going to subtract 20 from that to get, oh sorry, we're going to subtract 15 from that, not 20. We're going to subtract 15 from that to get 20. That's where I was going with that. So each of these is a 1 standard deviation jump. Again, we're going out 15, 15, and then 15, going 15 in this direction, 15 in this direction, and 15 in this direction. So, thanks once again to our handy-dandy rule, we can say we know that the area under the curve in between these numbers is equal to 0.997. With an area of 0.997, we can say we also have a probability of 0.997 and a 99.7% chance that between 20 and 110 items will be stolen from this store. All right, and that's all you need to know about the empirical rule, which is another name for the 68, 95, 99, 7 rule. I guess that was something more to know.